So in this tutorial, we're going to be coding a robot controller for the box challenge. Basically, we're going to try and write some code to make the robot travel in a box shape, just like it's doing right now. The point of this tutorial is to introduce some techniques that might be handy when it comes to the Erebus R competition. This is because the Webots robot controllers, as you know, don't run normally. They don't run sequentially. They have that one main loop that runs every couple milliseconds. So that might throw a wrench in some things, and you might have to structure your code differently. So in this tutorial, we will introduce some techniques that you might use for motor movements in the Erebus R competition. Links to the C++ code and Python code will be in the description, but Victor is going to do an explanation of the C++ version of this box challenge.
All right, we've demonstrated how to basically move forward straight ahead using the virtual robot. We're going to do something a bit more complicated now. Let's make the robot go in a square. So this requires both the gyro as well as the encoders because we need to know how to turn 90 degrees and we need to know how much we've actually moved. So to add, let's first add our gyro and encoders. So let's first add the include statements. So include webots slash gyro dot hpp and include webots slash position sensor hpp. And down here, we're gonna add our position sensor and gyro in the same way that we added the motors. So let's do gyro equals robot get gyro, and the name of the gyro is just gyro. And same thing for our encoders, which are called position sensors and webots. So position sensor, and we have one for our left motor. And notice how these encoders are actually attached to the motors themselves. So we say left motor get position sensor, and same thing for our right encoder. Equals right motor get position sensor. There we go. Now for the encoders and for the gyro, we actually also have to enable them because they're sensors. So down here in our int main, let's just do, actually above, we should have our time step because when we enable our gyro, for instance, by doing gyro enable, we need to pass the time step in. And same thing for left encoder, enable time step, and right encoder. All right, so now our encoders are enabled. And before I forget, I'm just going to set these velocities to 0 so the robot's stationary in the beginning. All right, so now the gyro in Webots, let me explain something. The gyro in Webots actually returns the angular velocity. So for those of you who don't know, the angular velocity is pretty much the rate of change of your angle. So we can't use that immediately. It's not going to spit out the angle alone. We actually have to do our own math here by integrating the gyro's value. And I'm sure not all of you know what integration is, but pretty much all we have to do is let's create a variable to store our angle, like double angle. All we have to do is, let's actually set it to 0 as well, is add on the amount of time that has elapsed times the gyro's current or instantaneous angular velocity. So we do time step And the reason why we divide time step by 1,000 is because time step is in milliseconds. So we convert it to seconds, and then we multiply it by the gyro's value. This specifically is around the vertical axis. So this tells you how much the robot is turning. And if you don't understand immediately the math, that's okay. You just have to know essentially how this works, and that will be fine. While we're at it, let's also create a function to get our current angle. So we're going to say double get angle, and all we're going to return is the angle. But note, however, that this angle is actually going to be in radians because Webots uh, returns its gyro value as radians. So we have to convert this into degrees, and it's easier to see it as degrees. So for those of you who don't know, 180 degrees is actually equal to pi radians. So all we have to do to convert it is multiply 180 divided by 3.1415, and that should be good enough. Now down here in our main loop, all we have to remember is to constantly be updating our gyro for every time step, and we should be good. All right, while I'm at it, I'm gonna add a couple more things up here, which you guys will eventually see why we need it, and I'm just gonna add it right now. So let's add a constant int max velocity. Pretty much, I'm just getting the max velocity that the motor is allowed to go at, or the max speed the motor is allowed to go at, and I'm storing that within a constant. And I'm gonna create a new constant called rad per meter equals 10.5. And what this rad per meter constant means is, say we want to have our robot go a certain distance, right? For instance, 1 meter. Well, there's no immediate function that we can use that's like go 1 meter forward. All the robot knows is based off of its feedback from its encoder how far it has gone. So the position sensor in this case is the encoder, and it actually gives its value back in radians. It doesn't give it back in distance or meters, it gives it back in an angle measurement, which is how much the wheels have rotated. And how we got 10.5 was we had to manually calculate it based off of here. This is on the Webots documentation page for the Pioneer 3DX, which is what robot we are currently using. You'll notice that it says the robot has 19 centimeter diameter wheels. And what that means is that we can find the circumference of the wheel, and therefore we can find out how far the robot travels in one revolution of the wheel. So the circumference of the wheel is pretty much pi times 19 centimeters, right? All right, and for 1 meter is 100 centimeters, right? If we do 100 divided by the circumference of the wheel, that tells us how many revolutions of the wheel we need in order to reach 1 meter. And since this is in revolutions, we can just convert that into radians, which is the unit of our encoder, by multiplying by 2 times pi, because there's 2 pi radians per revolution. Now, once again, if you guys don't completely understand this math, that's perfectly fine. Just trust us with this 10.5 number. Okay, a couple more things I'm going to add as we go along. I'm going to have an init angle, and you'll see why we need that later. And since we have to distinguish between when we're moving and when we're turning, because a box has 4 edges and 4 corners, right? So we have to turn at the corners and we just move straight during the edges. We have to distinguish between those two separate states. So I'm going to use an enum state. And if you never used an enum before, that's perfectly fine. You can just use an integer to store your state. And I'm going to have a moving forward state as well as a turn state. And let's call that state. And if we want to complete one full box, then we need to keep track of the number of edges that we traveled, as well as something we additionally need is our target encoder. You'll all see why we'll need this later, as I explain as we go along. So I'm going to write a go forward function, and that's going to take in a distance that we want to go forward. So the first thing in our go forward function is we're going to set our state to moving forward, and we're going to set our target encoder value to the current value of the left encoder as such, plus rad per meter. This is the constant we used before. We defined it as 10.5 times the distance that we want. And this distance is going to be in meters. So that defines, target encoder defines what our desired encoder value should be once we travel the amount that we want. And finally, let's just set velocity to max velocity 0.5. So this is going to set it to half of our max velocity. And same thing for the other motor. Great. We're going to do the same thing for a turn. We're going to write a do turn function. And let's have the state set to turning. And this is why we need the init angle variable that we created above. This is going to save our starting angle. And the way we're going to tell when we're finished turning is once our init angle and our current angle are as far as we want them apart from each other. So if the difference between our current angle and init angle is 90 degrees, then that must mean we've turned 90 degrees. And let's set the left motor to the max velocity times 0.1. So a tenth of our max velocity, and the right motor is actually going to go in the opposite direction by doing max velocity times negative 0.1 as such. So finally, we need two functions to tell if we're actually in the process of moving or if we're in the process of turning. So let's write a bool if forward function. This is going to tell us if we're in the process of moving forward. And the way we do that is if our destination encoder and our current encoder are not within a certain distance of each other, then we know we haven't reached our desired position yet. So actually, this is going to require that I use absolute value. So what I'm going to do is include math.h up here. And that will allow me to use absolute value. So down here, I'm going to say if the absolute value of the left encoder get value minus the target encoder is less than 0.1. So if the left encoder and target encoder are in a value very close to each other, then we can say that we've probably reached our destination. So let's set the motor speeds 0. And we're going to return false. That means that we return false when we're not currently moving forward. Otherwise, we just return true. We're going to do the same thing for the if turn. So we're going to say if turn if the absolute value of our current angle minus our initial angle is greater than or equal to, let's say, 86, then left motor set velocity is going to be 0 and right motor 0. So what this means is if our current angle is more than 86 degrees away from our initial angle, then we're gonna stop. That probably means that we've turned around 90 degrees. And the reason why I say 86 instead of 90 is the robot's gonna be continually moving. So it's gonna move a little bit even after you command it to stop the motors. So it's gonna move a bit more than 86, and that's probably gonna be around 90 degrees. And we're going to return false. Otherwise, return true. Okay, we're almost there with our program. So let's start off the program. It's immediately going to start moving forward. And that means we're going to set the state initially to moving forward. And we're going to call the go forward command. Let's make it go 2 meters. So immediately from the start, it should start moving forward. And then after our update gyro function call, we're going to check if we're moving forward or we're going to check if we're turning. So we pretty much set up a state machine here that alternates between moving forward and turning. So once it's done moving forward, it's going to transition into turning. And then when it's done turning, it's going to transition back into moving forward. So we're going to set the state. We're going to check if the state is equal to moving forward. And if the state's moving forward and we're not actually finished moving forward, or actually if we're finished moving forward, because then we're going to do a turn. Because if forward tells us if we're currently moving. So if we're not currently moving, then we transition into the next state of do turn. And then let's say else if state equals turn, if we're in our turn state and, oops, I can't press and, we're not turning, then we transition back into moving forward. But before we do that, since we only want to move in a box, we don't want to keep moving infinitely. That means that we're going to count the number of edges along the box that we move. Ultimately, this is going to come out to 4. And while it's less than 4, we're going to keep going in our pattern of alternating between moving forward and turning. So if you remember, we created a variable called edges traveled. And that's going to keep track of the amount of edges of the box we've traveled so far. So while or if num edges travel is less than 3, then we are going to increment num edges travel, which means we're traveling another edge of the box, and then we're going to do what we did initially, which is start moving forward again. All right, so now that we're done with that, and as long as I typed everything correctly, it should be good. Ooh, I missed a parenthesis right there. As long as I typed everything else correctly, it should build. So let's save that and try building. And at least the build is successful, so let's try resetting our world and seeing if it is able to go in a box. So I'll zoom in, and I'm going to run the simulation. Okay, so it's moving forward. And then it decides to turn, great. Yep, turns the second time. Third time. And great. So it actually did stop after the fourth turn, which means everything worked out as expected. And our program works perfectly.